Okay, so in this video, we will be seeing a problem where you have a train of 5 wheel loads which crosses a simply supported beam of span 24 meters from left to right. You have to calculate the maximum positive shear force, maximum positive and negative shear force at center of span, and also absolute maximum bending moment anywhere in the span. So the figure is already here. You can see this is a span beam. You have 24-meter span, and exactly at center, a point C is located at 12 meters from A, mid span. And this is a set of 5 wheel loads starting with 120 kilonewton. Then you have 180 kilonewton, 280, and another 80. Spacing is also shown. So the loads are moving from left to right on this beam. So let us start. First is to let us find the maximum negative shear force at center of span. So this is the position of loads shown. So we have seen in the previous derivations that in order to find maximum negative shear force, we have to place the first load at C and the rest of the loads to the left of section C. So that is how they are placed, and the corresponding ordinates are also marked y1, y2, y3 and y4. Now the maximum ordinate is given by yc, which is z by l. So referring to the figure, we can easily write that maximum negative shear force at C is nothing but 120 into yc plus 180 into y1 plus 200 into y2 plus 80 into y3 plus last 80 into y4. Okay, so now we have to find what is yc, which is the maximum ordinate. It is nothing but z by l, that is equal to 12 meter by 24 meter, or it is 0.5. Okay, then referring to from the principle of similar triangles, from similar triangle principle, you can write, uh, let's start with y1. So y1 by yc should be equal to, so these distances also you can mark. This is 3, 2, 3, 2. So 3, 3, 6, 7, 8, 9, 10. So this is 2 itself. So y1 means just this distance, y1 by yc means this distance by total. So 2, 2, 4, 5, 6, 7, 8, 9. So 9 divided by 12. Okay, which means y1 is equal to 9 into 0.5 by 12. Or you can keep it as 9 yc by 12, so that in the end you can take yc outside and then simplify. Similarly, second one, y2 by yc is equal to, y2 is here, so y2 by yc should be equal to this divided by total. So y2 till y2, the distance is 2, 2, 4, 5, 6, 7. So 7 divided by 12, which gives you y2 is equal to 7 yc by 12. Okay, then coming to y3. So y3 by yc is equal to 4 divided by 12, which implies y3 is equal to 4 yc by 12. Similarly, y4 by yc is equal to 2 divided by 12, or y4 is equal to 2 yc by 12. Okay. Now substituting, we can write therefore maximum negative shear force at section C is equal to, let us substitute in the equation we have written above. So I'll write 120 into yc. So 120 into yc plus 180 into y1 is nothing but 9 yc by 12 plus 200 into y2. y2 is 7 yc by 12 plus 80 into y3. So 80 into 4 yc by 12 plus the last 80 into 2 yc by 12. Okay. Now let us simplifying this, taking yc outside. So you will get 0.5 into 120 plus 180 into 9 by 12 plus 200 into 7 by 12 plus 80 into 4 by 12 plus 80 into 2 by 12, which gives a final answer Final answer you will get is 205.833. Okay, that is what I am getting. So please check. You will get the answer as 205.833 kilonewton as the maximum negative shear force at sea. Similarly, let's move on to find the maximum positive shear force at sea. So next one, maximum positive shear force at sea is equal to, you have to position the loads in such a way that the last load is at section C and all the other loads have crossed section C. So I'll again draw the beam. Let us draw the beam again. So this is your beam AB. This is the center span. So I'll place the last load, which is the 80 kilonewton load. Then the next 80 kilonewton load. After that, you have a 200 kilonewton load. Next 180 kilonewton load. And finally, you have the first 120 kilonewton load. Then we will draw the ILD also. So this is A, C, and this is B. Now the corresponding ILD, okay, and the ordinates. So this 2, 3, and 4. So this the spacing also was given 2, 3, 2, 3. So this is 2 meters, 3 meters, 2 meters, 3 meters. So this will be 2 meters. 3, 3, 6, 7, 8, 9, 10, 2 meters. Okay. So this is the critical ordinate YC, which is L minus Z by L. Let this be Y1. This is Y2. This is Y3. And this is Y4. Okay. We have to. So from the figure, we can directly write maximum shear. Positive shear force is nothing but 80 into YC plus second 80 into Y1 plus 200 into Y2 plus 180 into Y3 plus 120 into Y4. Okay. Then let us find the critical ordinate. Here YC is L minus Z by L, which is equal to 24 minus 12 by 24, which is nothing but 0.5. So from similar triangles, again, from the principle of similar triangles, we can write y1 by yc is equal to 3, 3, 6, 7, 8, 9, 10. 10 divided by 12, which gives y1 is 10 yc by 12. Similarly, y2 by yc is equal to 3, 4, 5, 6, 7. So 7 by 12, or y2 is equal to 7 yc by 12. Then y3 by yc is equal to 5 divided by 12, or y3 is 5 yc divided by 12. And finally, y4 by yc is equal to 2 divided by 12, or y4 is equal to 2 yc by 12. Substituting, you can write therefore maximum positive shear force at C for this load position is, substitute in the equation is already written, you have to substitute in that 80 yc. So 80 into 80 yc plus 80 into 10 yc by 12 plus 200 into 7 yc by 12 plus 180 into 5 yc by 12 plus 120 into 2 yc by 12. Okay. And finally, the answer which you will get, take yc outside, and the final answer which you are going to get is 179.166 kilonewton. Okay. Now, like I said, you have to check for one more trial because it's a set of point loads and we cannot, they are of different magnitude. So maybe you will get a maximum positive shear force when 180 kilonewton is to the left of C and the rest of it is on the right of C. So we will check one more position as a trial check. So another trial when the leading 80 kilonewton load is on C and the last 80 kilonewton load is to the left of section C. So we will check that position also. So draw the beam. This is beam AB. Section C is shown. So I'm going to place the second 80 kilonewton load here and the last 80 kilonewton load to the left of C. So that position was after 2 meters. Then after 3 meters you have 200 kilonewton load. After 2 meters you have 180 kilonewton load and after 3 meters you have the leading 120 kilonewton load. So this distance is 4. This is 12 meters. This is 12 meters. So 3, 4, 5, 6, 7, 8 plus 4, 12. Now draw the shear force diagram. So since one load is to the left of section C, that corresponds to a negative shear force. So I'm going to draw the ILD for positive and negative shear force. Okay. So this load is having an ordinate of y1 here. This is the critical ordinate yc. Then let this be y2, this be y1, and finally this is okay y2, sorry, y3, and this is y4. So this is 3 meters, 2 meters, 3 meters, 4 meter, and this is 2 meters. So this is 10 meters. Okay. So you have YC which is L minus Z by L for this triangle, and here you have a Z by L for this down triangle. Okay. So for this loading condition, maximum positive shear force at section C in this case is given by minus 80 into Y1 plus 80 into YC plus 200 into Y2 plus 180 into y3 plus 120 into y4. Okay. Let us find the ordinates. So Z by L is given by 0.5. Also L minus Z by L is also equal to 0.5. So in below triangle y1 by 0.5 is equal to 10 divided by 12, or y1 is equal to 10 into 0.5 by 12. Coming to the upper triangles, y2 by 0.5 is equal to 9 by 12, or y2 is equal to 9 into 0.5 by 12. y3 by 0.5 is equal to 7 by 12, or y3 is equal to 7 into 0.5 by 12. Then finally y4 by 0.5 is equal to 4 by 12, which is y4 is equal to 4 into 0.5 by 12. With these values, let us find the maximum positive shear force at C is given by minus 80 into y1, so 10 into 0.5 by 12 plus 80 into 0.5 plus 200 into y2, which is 9 into 0.5 by 12 plus 180 into 7 into 0.5 by 12 plus 120 into 4 into 0.5 by 12. Okay. So simplifying this, you will get a value of 154.167 kilonewton. So comparing the above value and this value, therefore maximum positive shear force at C is the value which you found first, which is 179.166 kilonewton itself. Okay, this is how you will find the shear force. In the next video, we will see how to find absolute maximum bending.